This is the mock exam solution for discrete random variables for applications. The Giants basketball team undergoes COVID testing before entering the tournament bubble. The probability that no team member has COVID is 0.8. The probability that more than 2 players have COVID is virtually 0. The probability that 1 player has COVID is 5 times more likely than 2 players having COVID. Complete the following probability distribution table for X, the number of players that test positive for COVID. Okay, so what we know is that there is a 0.8 probability that no team member has that has COVID. So that would be 0.8 in this first box, because X equals 0 is related to X players having COVID. And we know that the way that these two boxes are filled in is that the probability that 2 players have COVID, is, let's see, if it's X, then 1 would be 5X, because the probability that 1 player has COVID is 5 times more likely than 2 players having COVID. I'm going to change that this X to a K, because we already used X in this problem, right? And the other important thing that we always know is that a probability distribution table probability should add up to 1. So if we add up 0.8 plus 5K plus K, it should add up to 1. And then now we could make this into an algebra problem. 0.8 plus 6K equals 1. 6K equals 0.2. And then K is equal to 0.2 divided by 6, which is equal to 0.0333. And so for 2, we know that the value would be 0.333. And then for 1, it would be 5 times that, which would be 0.167. Keeping 3 significant figures, okay? Then it asks us to find the expected value of X. And the way we find the expected value of X in this case, because it is not a binomial distribution, right? We didn't use bin CDF or bin PDF here because it's not. Remember that what we need to do is we need to put the data values into L1 and we put the probabilities into L2, and then we can find the X bar value, and that would be the expected value of the variable X. So let's do that. We'll do stat, edit, and then we'll put in the numbers 0, 1, 2, and then we'll put in the probabilities 0.8, 0.167, and 0.0333. And then we'll do stat, calc, 2 var stats, L1 and L2 into XList and Y. I'm sorry, it's not 2 var stats, 1 var stats, right? Because we want to put L2 in the frequency list. There's only one data variable here, which is X. The L2 is just how often X occurs. So the answer would be the X bar value here, which is 0.234. Okay, 0.2335 rounded to 3 significant figures. Okay. All right, and let's go to C. Find the probability that there are 2 positive tests given that there is at least 1 positive test. And this is a conditional probability problem, which means whenever you see the word given in a probability problem, that means it's conditional probability. Go to the formula booklet and grab the conditional probability formula, which is the probability that A given B is equal to the probability that A and B both happen, which is A intersect B, divided by the probability that B happened. And in this particular case, we're looking for the probability that there are 2 tests positive, given that there is at least one positive case. So the probability that there's 2 tests positive and there's one positive case is the same thing as the probability that 2 tests are positive, because 2 tests are positive is included in at least one positive case. So basically, the top would be the probability that there are 2 positive tests, and the bottom would be the probability that there is at least one positive case. At least one case. Okay? So, and then let's find the values for those. So the probability that there are 2 positive tests is 0.0333, right? And the probability that there is at least one case, that would mean 1 or 2 cases, or more, but remember, the probability that there is more than 2 cases is virtually 0. So it would be 0.167 plus 0.0333, that would be 0.2. Okay, if we added those two together, we get 0.2. So the probability here would be 0.0333 divided by, and remember, this problem is actually not a binomial distribution problem, and it's not even a discrete random variables problem, but it's a probability problem, and probably when you get the discrete random variables problem or the probability distribution problem, they're going to mix it together with a probability problem, right? So the probability, the conditional probability here, which is 2 positive cases given that there's at least one positive case, is going to be 0.167. So what's the probability that you have 2 positive cases? It's very small, 0.0333. But assuming that you have at least one positive case, then the probability that you have 2 positive cases is much larger, 0.167, because you already know that you have at least one case. So the only possibilities are that you have 1 case or you have 2 cases. Okay? All right, let's go to the next screen. Next page. Once in the bubble, the Giants basketball team plays 7 other teams 1 time each. In each game, the Giants have a 60% chance of winning. Find the probability that the Giants go undefeated. Okay, so this is a binomial distribution problem because there's repetitions, same probability each time. Let's see. And there's 2 outcomes possible, winning or losing, right? So let's see. We know that the number of trials is the number of games, so that would be 7 games, right? There's 7 other teams, play each team once. And going undefeated, how many wins is that? That would be 7 wins. So x would be equal to 7, and the probability, of course, is 0.6. And should we do binomial PDF or CDF? Well, if they go undefeated, it's basically exactly 7, right? It's not like 7 or more or 7 or less. It's exactly. So exactly means bin PDF. So we're going to do bin PDF. Second distribution. Go to the second page. Bin PDF. 7 games. 0.6 chance of winning any game. And we want to win 7 games because we're going to go undefeated. So the answer is 0.027799. So 99 would round up to 80. So the third significant figure is this 0, the last 0 here. Okay, part B. Find the probability that the Giants win more than half the games. So in this case, the number of trials, again, is 7 because there's 7 games. The number of wins that we're looking for is more than half the games. So win more than half the games would be 3.5, right? So it would be greater than or equal to 4 games. And remember, the calculator doesn't calculate probabilities that x is greater than or equal to 4. It only does less than or equal to. So what we need to do is we need to calculate a different probability and subtract it from 1. So what probability subtracted from 1 would give us the probability that x is greater than or equal to 4? It would be the opposite case, which would be that x is less than 4. So, but we need to express it as less than or equal to, because the calculator does less than or equal to. So what would be x is less than 4 be equivalent to in the case of whole numbers? It would be less than or equal to 3, right? So what we need to do is we need to do x equals 3, and we need to do CDF because we're doing less than or equal to, and that's what CDF does. And finally, the probability is equal to 0.6 like it was before. So let's figure out that probability with binomial CDF. We go to the second page, option B, and we put 7, and we put 0.6, and we put 3, and the probability of the wins being less than or equal to 3 is 0.2897, and that rounds up to 290. So it'll be 1 minus 290, 0.290. 0.710. So 0.710 chance of winning half the games. Part C. Find the expected number of wins for the Giants and the variance. So if you look in the formula booklet, the formula for the expected value of x is n times p. And in this case, our n value is number of trials, and our p value is 0.6. So the expected value of wins is 4.2. If you put 7 times 0.6 in the calculator, you get 4.2. Okay? You could put 4, okay, if you want to say, oh, the number of wins has to be an integer, so I'm going to say 4. But 4.2 is fine. It's kind of like an average number of wins, so even though it doesn't make sense to have 4.2 wins in the case of averages, you can argue that it can. So you could say 4.2 or 4. What about variance? In the formula sheet, variance is given as NP times 1 minus P. So it's basically almost the same formula. You just have one extra number to write, which would be 1 minus 0.6. So it would be 7 times 0.6 times 0.4, which is going to be 7 times 0.6 times 0.4 is equal to 1.68. And the variance is kind of like how close are you to the normally how close would you be to the expected value of 4.2 or 4 expected wins. So 1.68 is the variance. And if you want to know the standard deviation, which we worked with in the past, know that variance is actually equal to standard deviation squared. So if we want to know standard deviation, we take the square root of the variance, which would be, and they didn't ask you this, but if you ever do need to take the find the standard deviation, it would be 1.30. Okay? All right, that's it for the mock exam.